Okay, so you're fortunate. This is the last video in this series of introducing VPython with Coulomb's law. And for this one, I've gone back to kind of the previous model that we had, where we had objects and we were just letting the first one move as a result of the forces that were acting upon it. But I did change things pretty substantially because now we have a third object, right? So you can see here that we've got this third object, and I'm not going to do anything crazy with it. I made it red as well, and it's going to be, at least in this case, identical to the second ball that we had created. Okay, so all the parameters I put there are the same. The only difference is that it's on the positive side of the x-axis rather than the negative side. So we've got the first ball at the origin, this a little bit to the left of it, and this one a little bit to the right of it. We'll start them off at time equals 0. I've got my delta t. I've named my output file as 3-body C for no really great reason, just because it's a 3-body problem now. We've got 3 objects in the system. And this is when things start to get pretty tricky. In my while loop, I have it going until we get up to 2 seconds, so it's actually going to do a lot of iterations. Now, to make life easier, what I did was this force here represents the force of charge 2 on charge 1. And it's just the same formula that we had before. It's exactly the same. This one is the force of charge 3 on charge 1. And it's the exact same force as we had for the other one, only we're now focusing on ball 3, the charge of ball 3, and the position difference between ball 3 and ball 1. There's also this negative sign. Now I put that in there because in this situation everything's moving along a straight line. So it's very easy for me to say that the ball on the left, this one, is going to repel, because they're all positive charges, at least for right now. So it's just going to repel this, pushing it to the right, so in the positive direction. This one, also positive, but on the right of ball 1, is going to repel it, which means pushing it to the left, and thus we get a negative sign. And then the net force is just when we add those two together. So it's a pretty simple idea. The ball velocity, this formula is unchanged, and the ball position is also unchanged. I didn't really do anything. I just changed the arrow scale slightly because some of the forces will be a little bit bigger and the space is a little bit tighter, but no big deal. And I'm going to plot the time and the ball's position. That's all that I'm going to do here. And the last thing that I'm going to do is just output all the data that I had previously outputted to an Excel spreadsheet. Just once again focusing on ball 1. Ball 2 and 3 will not move. So when I run it, that's awkward. So this is one of the fun parts of programming. Apparently I made a mistake in some manner, and now I have to debug, and that's most people's least favorite part. My suspicion is that I didn't update things properly because nothing was happening. So let's see, I've got the net force. Oh, I changed this a little bit from the previous case that I had been practicing on. Clearly nothing's going to happen because they're the same charges the same distance away. So what I'm going to do is I'm going to break the symmetry. So they were pushing equally hard in opposite directions. I could say that I did that intentionally just to show you, but I completely forgot what I had just done. And I thought I had it at this state. Okay, let's watch this again. Now it's a little bit more interesting, right? So it gets pushed to the right, and then it gets pushed to the left a little bit harder, so it goes in that direction, and so on. Now one of the things that's interesting is that you can see that the force is lagging compared to, and actually I should state this differently, the motion of the charge is lagging compared to the velocity or the force that's acting on it. And you can see the motion here, so this was just the position versus time. And it would be interesting, and we can actually do this, maybe I'll show you in a later tutorial. We can actually plot multiple things on the same graph. So we can have say position versus time and velocity versus time and acceleration or force versus time for the same object plotted on the same graph, which can show us some interesting patterns. The other thing is that you can just output all that data into Excel and graph it in Excel. Now what I'm going to want you to do first to start with is to play around with the different parameters. So I started it closer to the one on the left. What happens if you started a lot closer? What happens if you start this one a little bit closer, the one on the right? What if there's a difference in charge between these two? What if, well, I think you can probably tell what's going to happen if they're both, say, positive, or they're both, I'm sorry, if one of them's positive, one of them's negative, but try it out. See how the simulation handles it. See if it follows Coulomb's law as you would expect it to, or if there's a breakdown because of your iteration time or something like that. One of the other things that you can do is you can run this simulation, right, and you can get the data, and it pops out into Excel. And to help yourself see the patterns, what you can do is you can change this, and you can call this now, oops, you can call this 3-body C2, and then you can go up here and you can change some parameters. So let's make this one twice as big in terms of its charge. And then we would run it again, and we'd have the output into a new spreadsheet. Once you're done and you've tried a couple of different variations along the same lines, you can open up these spreadsheets, pull the data into the same file, and then just graph all of them on the same graph. And that's going to allow you to see what's the difference between them. Okay, and this is an important thing, because this type of a questions related to this exact problem that I'm showing you right now, show up quite often on AP tests. So it's an easy way for us to get started with getting an intuitive feeling for what takes place, what happens, what's important, and how the various things affect the motion. And hopefully you can think back to your previous physics days from honors physics, and you can recognize the motion that we were getting in this problem, which was simple harmonic motion. Okay, so continue to explore, and just make sure that you don't write over the spreadsheet that you did from a particular trial. Rename, and then once you're done experimenting, just pull all of the data together. If we need to, just send me an email and I'll make a tutorial of what I'm talking about, but I'm hoping that you can kind of figure it out. But if not, just send me an email and I'll help you guys out.